Here we go. I'll just let it record. So I believe let's just start with torque. Who knows what the formula for torque is? First, what is this? What's that symbol? Huh? Tau. Okay? Tau. Look at this. I think this might be a thing here. I forget. Tau is the symbol for torque. And if I'm not mistaken, torque is the cross product of the radius of something. I'll explain what the radius is with the force that's being applied. So consider a door like this, and you have some hinge like that, and you want to push the door to close it, let's say to a position like this. So you're applying a force over here, and that force happens to be a certain distance from the axis of rotation. And if this distance, this is what we call an R. So in most cases, when the force and the distance to this axis of rotation are perpendicular like this, since this here is the same thing as R F sine of theta, where the angle is this angle here, theta, for the most part, you'll just have to use R times F. The angle will be usually 90 degrees, so just RF is your torque. But you can see that if the angle was like, if my force was at an angle like this instead, then you don't look at the angle between R and F like this. You would extend the force and sort of draw it out like that. So this is my force. The angle between the radius and the force would be that angle there. And the reason why the force, the torque is a cross product is because the part or the component of the force that is along the radius is just pushing on the hinge, okay? It's like me trying to close the door. Let me go outside. And I'm like trying to close the door by pushing on it. It's not going to do anything, right? You have to push perpendicular to the axis of rotation so that the door can move. So essentially, by taking the sine of this force, right, the sine of that angle will give you this side here of the force, which is the component that actually will rotate the door. So in this case, whatever the angle is, you plug it in here, that will give you your torque. Now, welcome to the class. Okay. It's like 9 people there. Okay. So now I should also mention that the torque is also equal to this. So what are those two things? Can anyone say I alpha? You look very confused. Like, I is the moment of inertia of the object that's being rotated, and alpha is the angular acceleration that the object will achieve or will experience. Now if I write this, this is your Newton's law, right? Force equals mass times acceleration. The reason I put that here is you can see that there's a very close relationship between the torque and force equation. The torque, the actual torque, is determined from the... Oh, by the way, R is also called the moment arm. So it's like the arm, because it's like an arm, and the moment is the force that's creating the rotation. So sometimes they'll say the moment arm is 2 meters, and what they're referring to is the distance from the axis of rotation to the application of the force. Anyway, so once you have your torque, it's equal to I alpha, and I is the moment of inertia of the object. If you want to try to understand that in terms of Newton's law, basically the torque is the rotational equivalent of the force. Moment of inertia is the rotational equivalent of mass. And obviously, angular acceleration is the angular equivalent of linear acceleration. So, if mass is the resistance of an object to being accelerated, moment of inertia is the resistance of an object to being rotated. So, in general, the equation for moment of inertia looks something like this. R squared dn. So, pretty much, I mean, don't let that confuse you. It looks complicated. All it means is if you integrate an object, let's say you have an object like this, some blob, and you take a small section of it, and the distance to the origin, if you're trying to find the moment of inertia around the center here. So let's say this object is going to rotate like that. You would add up all the little pieces of mass and the distance to the origin and integrate over that, and that would give you the total moment of inertia. But I think for your class, you don't have to actually integrate. So you'll have something like, let's say you have, what's a simple case? I believe if you have, let's say you have this, you have a disk that has some radius A and an outer radius B. So this is the part of the disk. And this thing was being rotated around like a central axis like that. So the whole disk is rotating like that. Or you could also rotate it like this too. Like the whole thing is rotating that way. But depending on, in your book you have a table of moment of inertia. And I think for this one, the moment of inertia around a central axis is equal to, maybe, I think it's this, I can't remember exactly, mass times a squared plus b squared. You don't have to, you can write it down if you want, it's just an example. If you have, for example, a rod, you can rotate it around its center, around an edge, or you can rotate it around an axis that passes through its center, so it's rotating like this, right? So what I'm trying to get at is that depending on the axis of rotation that the object is spinning around, you'll have a different moment of inertia even though it's the same object. Whereas for linear motion, there's only one mass. No matter how you push it, you always use the same mass. Here, what matters is what axis is it spinning around. Even though you're applying the same torque on an object, depending on what it's spinning around, you'll have a different angular acceleration. So let's just do a quick example, so you can see how you would, let's say we had the problem here, okay? So now we don't have a force at an angle. I'll try to add actual values here. So we have a force of, let's say, 5 newtons, okay? And this whole thing weighs, the mass of this is, let's say, 2 kilograms. And you're applying the force at a distance of 1 meter from the edge over here. Does anybody have, I can't remember, can you open your book to the chapter and look at the table for a thin rod rotating around its edge? It might be a third mr squared, but I can't remember. Moment of inertia. So, do you guys remember what the relationship between, in the meantime, alpha and A is? Anyone? Bonus points if you get this? Oh, look at that. What? No, go ahead. If you can find it. What's the relationship between A and alpha? How do I get from A to alpha? Huh? Yeah, so I have linear acceleration. How is that related to the angular acceleration? It's related by one variable. No? R, exactly, the radius. So A is the linear acceleration is equal to R alpha. This stuff I've been explaining since the beginning, but they really start using it heavily in this chapter. But you should know that A is R alpha, B is R omega, and S is R theta. And actually, these two come from the first one if you derive. If you take a derivative of this, you get V is R omega. If you take the derivative of that, you get A is R alpha. S? S is, if you have an arc of a circle, the outside distance S is related by the angle you sweep, theta, and the radius R.
The same as B. Distance.
Yeah, it's a distance. It's just a distance on the outside of a circle. Let me see what this looks like over here. You could probably, yeah, you could see that on the big screen. You probably get to see. I should just write a bit bigger. Okay, so did you find that table? Let me see. So if you guys look, just to get an idea, you have different objects, and depending on which axis you're rotating them around, you'll have a different value for the moment of inertia. So So in this case, we have a rod. I can model the door as a rod. And it says the long thin rod with rotation axis through the end is 1/3 ml squared. Here you go, guys. So assuming the door is a rod, the moment of inertia for it is I is 1/3 ml squared. So that's the last piece of information we need. Now I have the force that's being applied. I know the distance from the force to the axis of rotation. It's pretty much a door just being rotated like that. I have the mass, and with that I'm going to plug it in here and find out what the angular acceleration of the door will be given that torque. So all we have to do, the angle between the force and radius is 90 degrees, so it will just be RF. So I'll just write it out over here. The torque will be R times F, which is 1 meter times the force, which is 5 newtons, or that equals to 5 newtons meter. Right? The units of torque. Anytime you want to find the units of something, just plug in directly, like for force, I plug in kilograms and meters per second squared. So the units of newtons are meters, kilograms, meters per second squared. For torque, it's meters times Newton, meters Newton. Okay, so now we know what our torque is. Our torque is 5 newtons per meter. If I want to find the angular acceleration that I would get, I just have to divide the torque by the moment of inertia of the rod, and I'll get the angular acceleration. Let's calculate the moment of inertia from here. 1/3, the mass I said was 2, so 1/3 times 2, and the length of this is really just the radius as well, so that's a meter, so 1/3 times 2, so the moment of inertia is 2/3. 2/3. So if I take my 5 newtons and divide it by the moment of inertia, which is 2/3, I would get 5 divided by, so I'll get 15 over 2. Right? 15 over 2. So our angular, so I'll write it out. Alpha would be equal to the torque divided by the moment of inertia, which is 5 divided by 2/3, or 15 halves, or 7.5. And what are the units of angular acceleration?
Radians over s squared.
Yeah, radians per second squared. Very good. Radians per second squared. Oh, we did. Who was here when we did simple harmonic motion? Remember, with like we had like x is equal to a cosine of omega t plus 5. You guys missed the simple. I'll try to do some simple harmonic motion as well, if we can fit it in. So I'll rush a bit more now. So here I have the angular acceleration. So if I want to calculate how much, let's say I was asking. What?
You wrote I is equal to 1/3
ml squared.
m.
Yeah, m the mass.
Oh, okay.
M is the mass. So if I have the angular acceleration, I want to find out how much, what was it? I said how much time it will take to close the door? Yeah, that's what I said. So let's do that. If we have our equations of kinematics, we'll have delta theta is equal to omega initial t plus 1/2 alpha t squared, right? So all it is, I took the regular equations of kinematics and replaced x by theta, v by omega, and a by alpha. So now the door starts from rest, so I can cancel out this part because omega initial is 0. The door has no initial angular velocity, and I know that the door is going to be going through an angle of how much is this angle from here to here? In radians.
Pi over 2.
Pi over 2, yes. So I want to solve for the time. So 2 delta theta divided by alpha square root is equal to the time. And so square root of 2 pi over 2 divided by 7.5 will give me the time that it would take to close the door, given a force of 5 newtons applied a meter away from the axis of rotation. So that's pretty much all of the torque will work like that. What, you look confused?
I don't get the
What I did? I just used the equations of kinematics, and I wanted to know, for the door to go from here to here, I know that that will rotate through an angle of pi over 2, because that's not it.
energy.
Huh? No, I haven't used energy here. I've only used the equations of kinematics, knowing, and I know the acceleration it's going to have. Okay, you know, remember this? Delta x
Okay.
initial t plus 1/2 at squared.
Okay.
I just used that by using angular terms, and then initial velocity was 0, then I want to solve for the time. This is moving.
So you cancel the height?
There's no height.
So that's why you cancel
This?
Yeah.
This cancels because this is an angular velocity initial. And because the door starts from rest,
Okay.
the omega initial is 0. That's why I just left it out.
Okay.
And then I just solve for t. So I forget the answer, it was some random value, it doesn't really matter. Now, I could do like a ton of other problems, but I just want you to understand the concept, practice some more problems like this, and you'll get torque. You'll see it's not so bad. Obviously, if you want to know, once I found the time, if I want to know how fast is the door moving at this point, I can calculate the angular velocity using, let me write a bit bigger, using omega final is equal to omega initial plus alpha t. So now I know how much time went by. I know the angular acceleration. The initial velocity again was 0. I can find out the final angular velocity of the door at that point. Okay? So that's pretty much it for how torque works. You have the torque is the radius crossed into the force, and that is also equal to the moment of inertia times the angular acceleration.
Today we did some things on like the seesaw.
Oh yes, the seesaw. What?
Center of mass.
Yeah, center of mass. So let me do another problem. I'll do like 2 more problems that will cover those topics. Should have recorded this from the start. It actually looks really good, surprisingly. And then people who can't attend would see all the class. Alright, so let's do another problem before I get to the seesaw thing. I want you to see how we can do the same thing using energy, okay? So let's say I have, in this case, I have a rod, again, like that, and the rod is being held up horizontally, and then I drop it, and it's going to rotate like this, right? So this is what the rod will look like after, and it's going to be swinging this way with a certain omega final. Wake up! It's okay. This problem will really like reinforce the whole torque / rotational motion thing. And yeah, bring your coffee, guys. It's good. I just had a huge coffee on the bus. If you can tell. So omega final, I'll just call it omega. I'm already doing omega final. Now in this case, what's causing the rod to fall down? There's no force that I'm not applying a force. I'm just letting go of it. Gravity, right? So if you had to guess, where is the force of gravity going to act on the body?
The initial thing is on top of it.
Yeah, it's here, and it's something is holding it here. Like I'm holding it like this, and I just let go, and it's going to fall. But I'm holding it, so it's imagine a long stick that I could just hold like that and it will fall, or my hand. That's pretty much it. My shoulder is the axis of rotation. So clearly, gravity. You can model this as a point mass, having all of its mass centered at the origin, at the center of mass. Okay. So basically, anytime you have an object rotating, if there are forces on them, they'll be shown. But as far as gravity is concerned, it always acts at the center of mass. It's not that it actually acts there, but it will behave in the same way as if the mass was all concentrated here. So this would be our gravity, would be force is the weight F mg. So if I had to use my torque equation, I would write the torque is equal to the force of gravity times the radius, which is half of the length in this case. But for this problem, we won't actually do it like we did the door question. We're going to use energy to solve it because it's just a little bit more complicated.
But
So,
I have a
yeah.
question. Well, since the point in the middle is the center, how come the radius is at the center of that whole thing? Isn't the radius supposed to be the whole thing that's rotating upon the axis?
Okay, this here is the length. This here is the radius. And the radius is just the distance between the force that's being applied and the axis of rotation. So if I had a force acting here as well, like this, my total torque would be equal to, so anytime you have a force that creates a torque that rotates the object clockwise, okay? You know how you have like right is positive and left is negative? Basically, clockwise is a positive rotation and counterclockwise is a negative rotation. So, which way is the gravitational force going to rotate this? Clockwise. So that would be positive. So if I have to write out my net clockwise, right? This will make it rotate like that. So if I have to write a net torque, I would write plus the force, which is mg, times the distance to the axis, which is L over 2. And then this one is rotating it counterclockwise, so that's negative. So minus the force times the distance from here to here, which is just L. So if I had, what? You're like, huh?
What? No, like, I'm learning this at 6, so like, I haven't seen this before.
You're learning this at 6?
Yeah.
So learn fast.
Why?
All I'm saying is, if you have a force acting on an object, to find the torque that force exerts on the object, you multiply the force times the distance from the force to the axis of rotation. So that's why for this one, the gravity is acting at the center of mass. That's something I just said. The force of gravity is mg. The distance from here to here is the total length divided by 2. So that's why I did mg L over 2. And because gravity would be rotating this clockwise, I made it as a positive torque. And what's that? And this force here is acting at the edge. And since this force up would rotate it counterclockwise, I put it as a negative force. Yeah, well, she had a question first.
You don't think it's counterclockwise, it's positive?
No, it's negative. If it's clockwise, it's positive. If it's counterclockwise, it's negative. Is it? No. Didn't I say the opposite? I thought I said clockwise is positive, counterclockwise is negative.
I know, but he says.
Oh, he's saying that. Okay, maybe I just messed it up. If that's the case, then just flip this over. My bad.
Does it matter?
It's really just a convention. As long as if you flipped it, the answer would be the same, but you would be giving like let's say you got a negative answer and you were using his convention, he would assume that you were using the other convention. So it would it wouldn't really matter as long as you were thorough with it and always use the same thing. So if that's what he said, just use that. So here's the difference. Now would be this.
So is that for counterclockwise?
Yeah. So this is pushing down, so it rotated clockwise. So I put that as negative, and this force is pushing it counterclockwise. So that's positive. So if this equaled this, then there would be no torque. The thing wouldn't rotate. Which makes sense. I think you were first.
What force is pushing it up?
Some force. This is just, it could be me, yeah. It's not, gravity is the only one that acts in the center, although I could have put a force, an external force here. I just wanted to show you that if there was some other force, it would work like that, yeah?
Okay. You know how L is over 2? Can you also put 2R and then have FR, like,
Yeah.
in the system?
FR, you mean? I could have written this as,
Like if L is 2R, can you, instead of having L over 2 and FL, can you, like depending on your unknowns, can you just...
yeah, you could use R. If you wanted to call this the total radius, then this would be R over 2 and this would be R. It would work as well. I just chose L in this case so you can see. Sometimes it'll be R, sometimes it'll be L. It really depends on the problem, yeah?
Okay, so torque is force
Times distance.
times distance. But what's the FL for the plus FL?
It's because I have the gravity here and I have some other force pushing up here. And this force is acting a distance of L away from this point. So to get the torque that that force creates, I just use F times L. Whereas here, the gravitational force is acting a distance of L over 2 away. That's why there's an L over 2 in that computer here. Yeah?
Can you do like area?
What area?
Like FL would be like base times height and area would be like over 2, so it'd be like a triangle?
No, there's no area here. It's not like when you have the work was force times distance and you have some graph and this is the area underneath. No. All it is because that would be what the equation for work is. 1 second. So it's all because if you push on an object, the closer you get to the center or the axis of rotation, look at this door here. I'm going to push the same amount. See here, it's kind of closing a bit. But if I push way on the side, the same push is going to have a greater effect. If I push at the center, on the axis of rotation, the door isn't even turning anymore. Look, I'm pushing really hard. The door is barely turning. That's because, in terms of my torque, is RF. If the radius is 0 from the force to the axis of rotation, there's no torque. All I'm doing is exerting a force on the door. I'm not actually creating a torque in this case. The further out I go towards away from the axis of rotation, the same force has a much greater torque, and therefore a greater angular acceleration.
Okay, so when you did plus FL, that's torque 2 since it's F.
Yes, these are two torques.
How come L?
This is one torque, this is the second torque 2, this is the net torque.
Okay, but then how come you're not taking the radius? L is not the radius.
It is the radius. Look, here I said the radius for this force to here is R. The radius from here to here is this radius.
Okay, so the radius is dependent on where the force is.
Exactly. That's what I've said the whole time. I'll say it again. The torque depends on the force and the distance from where the force is applied to the axis of rotation. So from each force applied at a different point, you have a different distance from it to the axis of rotation. So it always depends on where the force is being applied. If I push here or here, the moment arm or the radius is from here to here or from here to there. Alright, so all that was just to show you how the direction for torques goes, okay? So if you have multiple forces, you add up the force times the distance to the axis of rotation, and you do plus minus depending on whether it's clockwise or counterclockwise. And yeah, you
So
have
for a seesaw question, with the like fault from the center.
with what?
The fault, like the axis, like the whatever you want to call it.
Yeah, around the center.
Yeah, like is it still going to be counterclockwise or clockwise? Or are you going to do mass and see which way the direction goes?
Well, you would do that, but then the mass would create a force, and then from that they would apply a torque, and you do plus for the counterclockwise, minus, and then see which one's bigger and get the net torque. I'll do the question. I just wanted to finish this because then when you do that, you're going into statics, or where the whole thing is either moving or if it's in equilibrium, then the net force along x-axis and y-axis and the net torque should all add up to 0. So let me just finish this problem and then we'll get into that. I'm going to erase this for now. So here we don't actually have to look at the torques. What we're going to do is say that we're going to look at the energy, okay? So here, the rod has a certain energy, E, initial, and at the bottom it has some other energy, E final. Okay? Let's look at the center of mass of the rod. It's here. So if I do that, the center of mass is initially here, and let's say that this height here is 0. That's our I'm using energy, right? So the potential gravitational energy is mgh. So if I call this 0, from this height over here is a certain height which is equal to the length over 2 up from here, right? So this is L over 2. If the rod falls like this, its center of mass will move from here to here, and the the actual distance that the center of mass falls from here to here will be equal to half the length. Everybody okay with that? It's pretty clear, right? Now, in the previous question, I had a force applied, and And from the force, I multiplied by the distance, and that gave me the torque. And from the torque, I had I alpha, and I could solve for the angular acceleration. Using that, I used the equations of kinematics and found how much time it took for the rotation or whatever. Now in this case, we have to do it using energy because the angular acceleration of the rod in this case is not constant. In that other problem, there was only one torque and it gave you one angular acceleration. Here the angular acceleration is not constant. Can anyone tell me why it's not constant? The only force we have is mg. So why isn't the angular acceleration constant? As the rod falls, which way is the force pointing? Is it changing or is it staying the same? Gravity is always what? No, it's staying the same because even though the rod's falling, the gravity is always acting down.
So there's still supposed to be that force.
Oh, no, that force isn't there. That was just in the previous problem.
Okay.
Yeah. So gravity is still acting down on it. But look, I'm just going to show you a case where the rod is at somewhere in between. Okay, so you can see why this won't work. If this is the rod there, at that point, there's our force, mg. But if I wanted to calculate the torque at this point, I would have to do torque is equal to r cross f, or r mg, the force, times sine of the angle between them. So here's this. My radius is this thing here. Even though this is the actual radius from here to here. But the angle between the vector of the radius and the force is this angle in here. Now, you can see that when the rod was horizontal, the angle between the force and the radius is 90 degrees. So sine of 90 gives me 1, and I have the maximum torque. As this falls down, the angle becomes smaller and smaller until at the bottom, the radius and the force the angle between them is 0. So basically, because the angle is constantly changing as the rod rotates, I have a constantly changing torque. And since the torque is equal to I alpha, as my torque decreases, my angular acceleration is also decreasing. So your angular acceleration is constantly changing. So if I try to use the same equation as before, alpha t squared, I can't calculate the time using this because alpha is changing the whole time. So you can't use these equations. That's only when you have constant linear or angular acceleration. So that's why we're going to have to use energy terms. So, what are the 3 types of mechanical energies? There's actually 4, you could say. Just one? Name one? Thermal, right? Thermal is actually a separate, it's not mechanical, it's thermal. So, in mechanical you have kinetic energy, potential, gravitational potential. You have the energy of a spring, so the spring's potential energy, and you have kinetic rotational energy when something is rotating. Okay? So, I'll just write it down. The kinetic energy is 1/2 the mass times the velocity squared. The rotational kinetic energy is 1/2 the moment of inertia times the angular velocity squared. See the similarity? Mass, moment of inertia, velocity, angular velocity. The gravitational potential energy is mgh. The spring's potential energy is 1/2 k delta x squared. And that pretty much accounts for the main mechanical energies that you have. So here we have a mass. Let's just look at the center of mass. It's a certain height above the ground, this is what we call the ground. Even though that's not really the ground, we're saying that's our 0. So because it's at a certain height, it has some potential energy, some gravitational potential energy. So I'll call that UGI. Your teacher might be using different subscripts, but I've been using this throughout the semester, so I'm sticking to that. The rod starts from rest, right? So there's no kinetic energy because it's not. It's just starting from rest. There's no spring, and That's the only energy initially, is gravitational potential energy. How much energy does it have? Well, mgh. The mass of this is given some mass. So m times g, and the height. I'm going to erase this drawing. Everybody got this? The angle thing, this can all go too. That was an explanation of why the angular acceleration is changing. So mg, and the height above the ground as shown is L over 2. So L over 2. That looks kind of messy. 1/2 mgl. Okay? Because L over 2. So that's our initial energy. Now, when the rod falls down to this point, the center of mass is at height 0. So even though if this was our reference point all the way at the bottom, we would have some potential energy. Because I've chosen this to be the 0 level, there will be 0 potential energy at that point. But the rod is spinning, so it has some amount. Technically it has kinetic energy as well, but I'm going to treat it as rotational kinetic energy. So the energy that it has there is kinetic rotational. Here, E final is just K rotational, which is 1/2 I omega squared. Now, because gravity is a conservative force, there's no friction. We're assuming there's no friction between the axis of rotation or the hinge. So energy is conserved. So whatever initial energy I have in the system should equal the final energy when the rod is at the bottom. So I can pretty much equate this to this. Equating the two, E initial equals E final, gives me that 1/2 mgl should equal 1/2 I omega squared. From the previous question, we already have the moment of inertia of a rod rotating around the axis on the end. It was 1/3 mr squared. So I over here is 1/3 ml squared, if we want to use the same. Usually, when you have like an object that has a certain length, we'll call it ml. And if it's like a disc or a sphere or whatever, then you'll use r instead, since it has a radius. But really, it's interchangeable as long as you call it, you're referring to the same thing. So here you see we have, I'll use small m, so it doesn't confuse you with this m. So it's the same mass. And we know the mass, we know gravity, we know the length. We know the moment of inertia. So if I just put everything on one side, I can solve for omega and get the angular velocity of the rod at the bottom. And that's the problem. Yeah?
So you put 1/2 over there because of the radius?
Yes, because
the L divided by 2.
Yeah, exactly. I just didn't want to have mgl over 2. I put 1/2 in front so it looks neater.
Can you do just mgl over 2?
Yeah, I could.
I don't get like electrical. Okay, no. Sorry.
Yeah, so this energy equals the final, which is just rotational. Instead of kinetic, I'm using rotational, and I equated the two and then solved for omega.
Okay, and we didn't use L because the force is coming from the radius.
Because what?
It's coming from, we're just using gravitational right now.
Yeah.
There's no actual force.
Yeah, there's no other forces. The only force is gravity, and gravity acts in the center of mass. What? Oh, okay. Are you taking me off? You got it. Oh yeah, damn class. Students. Okay, well the seesaw, I was about to do the seesaw question, but
I'll get notes from her.
no, you just watch the video later.
Oh, where's the video?
Go to facebook.com/physicsgradesavers, all one word.
Okay.
Physics Gradesavers.
Sounds good.
I might have to chop it into pieces because it's going to be long, but you'll see the parts
Okay, thanks.
later. Okay, so let's do the seesaw question. Actually, I don't even know what the exact question is, but you guys have all of this? Okay. So, if you have a problem where you have multiple forces and some axis, in this case a seesaw, let's just pretend the seesaw looks like this, okay? And you have one person sitting here and a smaller person sitting over here. This guy has mass m, this one has mass, actually this guy has mass big M, this is small m. So, The problem might be stated like which way does it spin, or with how much angular acceleration does it spin. So obviously this guy here is creating a force mg. This guy here is creating a force big mg. Both of them are acting a distance of L/2 away from the axis of rotation, which is the center. So if I wanted to find the net torque on this, I would say net torque is equal to, and I would add up, the same way when I'm looking at the net force, I add up all the forces. Here when I want to find the net torque, I add up all the torques that I'm seeing. This here is technically applying a force up. This support is applying a force on the seesaw upwards, but because it's acting at the axis of rotation, that force creates no torque, because the moment arm is 0. Okay? So we can ignore that. And usually when you're dealing with problems like this, if you have multiple forces and you would choose, I'll explain later, but you would choose an axis around which one of the forces is 0 to evaluate your net torques. But in this case, you don't have to do that. So that only applies when you know that the system is in equilibrium. In this case, they didn't say this is an equilibrium, so I have to evaluate it using this approach here. So the net torque would be what? We said that counterclockwise is positive, and counterclockwise, and clockwise is negative, right? So this force here would rotate the seesaw like that. So that's counterclockwise, and that would create a positive torque. So the torque that this creates is the force times the distance from the force to the axis of rotation, which is mg/L/2. And that's positive. So I write mg/L/2. And the other force here is creating a torque that's clockwise, that would be negative. So that's minus big M g/L/2. So now if I actually had masses, I could plug them into here. And let's say this one was, let's say this mass was 2, this mass was just 1, so, and the length was 1, so get my net torque is 1 times 9.8 times 1 divided by 2 minus this mass here was 2 times 9.8 times 1 divided by 2. So really I get 9.8 over 2, which is 4.9, minus 9.8, which is minus, minus 4.9.
Okay, so you said the big M, it's going clockwise?
Yeah, you see, just think about it. If you're here and you sat down, wouldn't the thing would go like this? So that's, because that's clockwise, that we have as negative. That's why I put it in here as negative. So once you find that, you could relate the net torque to I alpha. But here for I, you would use the moment of inertia of a rod spinning around the middle. So from your book you could find that, and you would use that to find your angular acceleration. So if this was actually spinning, you need to know the mass of the rod in order to calculate, or the seesaw, in order to calculate the angular acceleration. And let's do a similar problem, but we're going to look at a question where the problem is in equilibrium. So this is clearly not an equilibrium, right? This is heavier than that. So let's do the same thing. Can I erase this? Is that what you did? I don't want to erase it, I just want to change it actually.
So the whole bar you said is like what? It's a meter or something?
Yeah, the whole bar is a meter, exactly. Oh, so actually here for the length, I already took it into account, yeah. I did half. The whole bar was 1, so that's why I used 1 in here. And they're both acting a distance of L/2 away. So that's why it's 1/2, 1/2. Alright, so look at this. I'm going to erase this. Now I'm going to do the same question. Okay? But I'm going to put in a force over here. Okay? So this is more like what you will see in the class when you're dealing with systems in equilibrium. So if I put a force there, I will tell you the system is now in equilibrium, which means it's not moving left or right, it's not moving up or down, and it's not rotating. Okay? That's what equilibrium in this case would mean. So what the question would ask you is, what is the force required such that this whole thing is not, is in equilibrium? Or they would give you the force and say, at what distance from the axis, from the center, should the force be applied so that the whole thing is in equilibrium? So do you want to do it with the distance or the force? Force? Okay. So how much force should be applied? Is that what you're saying? It's either or. In this case, I will tell you that this force is at a distance of L over 4, right? Because it's halfway through. And so I'll ask you to solve for how much force is required. Let's do it over here. So I would say, oops. The sum of all forces along x equals 0. The sum of all forces along y equals 0. And the sum of all torques equals 0 as well. Yeah?
That's probably
Yeah, this is like your new rules for all the problems when it's in equilibrium. So for equilibrium, you got that. And that makes sense because the thing is still, you know? If you have a bridge or whatever, the bridge isn't moving, it shouldn't be moving. And the net forces and torque should all add up to 0. So in this case, we only have one unknown. So you only need one equation to solve for the force. In other cases, you might have a force applied at an angle, let's say at some angle like this. And it would say, at what angle should that force be applied? You have to solve for the angle and the force. If you have two, then you have two unknowns. So because the force is an angle, it will actually push the whole thing sideways. So this support here will have to somehow add an opposite force to oppose the motion. And that's where you would use the equation for Fx is equal to 0. So you add up the force, the component of the force that's sideways will go in x, and the other component that's vertically will go in the y-axis, and you equate all the forces along with the torque that creates, and when everything adds up, you'll be able to solve for either one. But in this case, all you have to do is add up our net torques. So you can pretty much use the same equation. We had the net torque was equal to, and then you have mgl over 2 was the counterclockwise one, so that's positive. mgl over 2. We have minus big mgl over 2. And then what's the next term going to be? The next term?
Plus the force.
What's that?
Plus the force.
Plus the force, yes. So plus the force. And what else? It's not just the force, right? What? L over 4, yes, exactly. L over 4, because this force is acting on the rod a distance of L over 4 away. And then all of this, I would say, equals 0. And now I know mgl, I can solve for F.
I don't understand the L over 4 because the torque is force times the distance of the forces. Oh, okay, makes sense.
And it's here. If this is L, this is L over 2, so this is L over 4.
Okay.
Yeah.
Okay.
Don't be sorry, it's okay. I hope this helps. Take care. Bye. One by one. Another one bites the dust. Who's leaving next? You, okay, see? So fine. That's cool, that's cool. So did you guys get this? Because everything adds up to 0, you solve for F and you have your answer, yeah?
So if the force was on another way, it would be minus, right?
Yeah, if the force had been here instead, I would have put minus, because it would have rotated the other way. And then you solve it the same way. And that's pretty much all the way you would do it. If there was more stuff, you would just add up. If I had another force, like if one was acting, let's say this way, I would have another force somewhere maybe acting this way, and then maybe there's a force pushing here. This one would create a force up, and you have to add up the y, the x, and chose the torque as being around the central point here, okay? Because I did that, I have to take into account this torque, this one, and that one here, all three. What I could have done instead, I could have looked, because it doesn't matter which point you take, the torque around every single point should add up to 0, right? Even if I took this point here, this is not rotating, so the torque around that point should still add up to 0. So sometimes, what I was trying to say earlier, is it's easier to choose a point where there's already a force, so you don't have to take it into account. Obviously, I wouldn't choose this point, because then the torque of this force around it would add up to 0, and that wouldn't really help me solve for it. Right? I could have chosen this as my point, even though this is not the axis of rotation. I'll just say I'm looking at the torque around here. The net torque around the point should equal to 0, but because this force is acting at that point, I don't have to take that torque into account. Then I would have done force relative to here. Again, this is L over 4, but now this is rotated clockwise, so I'm going to put that as negative. And the only other force I have is this one here, which is L over 2 plus L over, actually L away. So it will be big mg times L, and that's also rotating it, clockwise. So the equation would look something like net torque is equal to F times L over 4 minus big M G L equals 0. Then I'll just put this on the other side and solve for F. So you see that I would get the same answer for F if I did this as I would for here, because this and this I think will give you FL over 4. Either way, the point is, if you have a more complicated problem, choose one of your points that you're using, looking at the net torque around, to be a force you already know, so you have one less thing. Or if you have two unknowns, you can choose one of the points as the point where the unknown is, so you eliminate one unknown and you can solve for it easier. Because you know the total should still add up to 0. Is this thing still going? Yeah. How long? It's been 52 minutes. Okay, so I think I'm pretty much done with this. I'm going to briefly try to cover simple harmonic motion so you guys get more out of this. And then next time, try to do some problems and you can ask me questions on it. That's your equation for simple harmonic motion. See you later.
Thanks, man.
Yeah. You were here for that one, right?
Yeah.
Yeah, okay, great. So you're not missing out. Later.
Later.
B is actually I won't write it out yet. I want you to understand the first one first. So if you have
So X is position.
X is position, A is amplitude, cosine is the cosine function, omega is the angular velocity, T is time, and phi is the initial phase angle. Okay? Initial phase angle. So, let me just think of a good way to explain this to you. Okay? Let's say you have a wall, and you have a spring, then you have a box here. Okay? So, and then I take this box and I call it 0. And I pull the box a certain distance over here. Let's say like that. I pull a certain distance d from here to here. And I let go. The box will be pulled this way by the spring, right? Then it will move past the origin to over here and compress the spring. And as the spring gets maximally compressed, the box will eventually come to a rest. And the spring will push in the opposite direction. And the box will start moving back this way. Because there's no friction on the ground, the box will oscillate back and forth. And this is what we would call a simple harmonic motion, because it moves back and forth in a way that matches a sine function, or in this case a cosine function. So the parameters that we have is d, is the distance that I pull it. So because this will keep moving from d to minus d to plus d, that will essentially be the amplitude of the motion. So if I have to draw it, here's a cosine function, right? It looks like this. Kind of like that, more or less. And cosine goes from minus 1 to plus 1. So all of this here is oscillating between plus minus 1. Now, if my amplitude was 1, my maximum displacement x would just be plus minus 1, because 1 times minus 1 would be plus minus 1 would be minus plus minus 1. If my amplitude is something greater than 1 or smaller than 1, it will essentially stretch or compress this wave to having a different amplitude. But what I want you to understand is that this thing corresponds to, if you flip this sideways, okay, look over here. If you flip this sideways like this, it would look like, let me do that actually so you can visualize it better. If I were to flip it sideways, I would have this. Kind of like that, right? This is our sign. Here's plus 1, here's minus 1. So what this corresponds to is, if my box is here initially, when I let go, when I started, the box is here. Then the box will start moving this way. So it'll go this way until it reaches this end. Then it'll come back and do this, like that. And here, this axis is time. So what this equation gives me is, with time, what the motion of the box back and forth will look like. What?
Because on our assignment, we had this thing that told us like it's almost the same thing as this one, and it was asking if it was accelerating or not.
If it was what?
If like which points.
Oh yeah, it's accelerating. I'll explain the acceleration in a bit. First, I want you to get, is this the going? It is. Okay. What I want you to understand is that even though it's a wave, it looks like some kind of cosine function. All this means is, if I wanted to know where the box was at the time, let's say, of 2 seconds, this graph will show me that at 2 seconds it's at the origin, for example. Because the box is just moving back and forth. And this showed me with time where the box is. So at 3 seconds, which might be over here, the box is at minus 1. So all the way over here. Now the box, this motion can be characterized by a certain frequency. Right? Every wave has a frequency. And the relationship between angular velocity and frequency is that it's 2 pi f. So in here, the omega is the angular frequency, or angular velocity, whatever you want to call it, of the motion, and that's related to the frequency by 2 pi. At the same time, the period of the motion, actually the period, t, is equal to 1 over f. So, if you have the frequency, you'll be able to find the period. And omega is equal to the square root of k over m. So if you have the spring constant of the spring k and divided by the mass of the box, which is m, you will, independent of how far you pull the box or the amplitude that you give it, this thing has a certain mass and a certain spring constant, so I have only one angular velocity. And so the frequency is set by the mass and the spring constant, and so is the period. So it's independent of the amplitude. Alright, so basically, now you know what omega and a is. X just tells you where this is. So this is x-axis here. So plus 1 or plus minus 1 x will be your position of the box. And the only thing you have left now is phi, okay? So phi, the initial phase angle, is by how much should I move this wave around so that the cosine function matches the initial position of my box. If my box is over here, when I start, if instead of sliding this way, I slide it this way and let go, you see that a cosine wave looks like this. But for it to match my case, I would need to start actually over here, because my box is on this side, then it goes from here. So if I slide this over by half a wavelength, or pi, then I will have the correct, my cosine function will match the actual case here, where I'm starting from the left. If I start at the origin, and I'm moving to the left, so if I pushed it this way, I would want to start over here, and it's moving to the left. Whereas if I was at the origin and it's moving to the right, I would want to start here, and then it's moving this way. Does everybody see that? This is at the origin moving to the right, this is at the origin moving to the left, this is at the right moving to the left, this is at the left moving to the right. So that was pretty intense, but it's very important that you have a correct matchup. Now, the way to find the actual initial phase angle, because it could be some random amount like here, is you basically say that initially, because x is any point, and if initially x is equal to 1, then I would say 1 is equal to, and I know that the box starts at the right side, plus 1. My amplitude is 1, right? Because it only goes from plus minus 1. We take the absolute value. So I'll say 1 equals 1 times the cosine of omega is just the square root of k over m. Right? That's omega. T is 0 because time is 0 at the beginning. So when I put a 0 in here, this whole term cancels. And I have plus 5. So you see, if I just put everything on this side, I pretty much just have 1 is equal to cosine of 5, or 5, oopsie, that's not a 5, that's a theta. Or theta is equal to cosine inverse of 1. What? Is it because it's going?
No, I said theta.
Again? Phi is equal to cosine inverse of 1. So, from that you would have your phi, and you could use that for your problem. Now, what's cos inverse of 1? Try punching that into your calculator. But make sure that every time you do this in simple harmonic motion, you have to be in radians, okay? Because this is all based on radians. If you're not in radians, it just won't work. You'll get wrong values. So always be in radians, but for other problems in degrees. What'd you get? 0. So why does that make sense? Because our box is to the right, and that's already a perfect cosine function. I don't have to add an extra amount to shift it. If my box is initially over here, it's initially at minus 1, right? So here I'm going to put minus 1, and I would have to solve for phi. I would have minus 1 cosine of this, or theta would be cos inverse of minus 1. What's cos inverse of minus 1?